It's Jeff Hansen again. Today I'm going to be talking about enzymes, and specifically I want to clarify how enzymes work, and I'm going to demonstrate this with a very familiar enzyme, hexokinase. And then I'll look at the coenzymes, which I've been talking about recently, and I will describe how some of them work in specific enzymes. So let's begin by just looking at a chemical reaction. Say that we have two compounds, A and B, and they undergo a chemical reaction and form C and D. And in fact, let's consider it a nucleophilic attack where the nucleophile is shown in pink and the electrophile is shown in blue. Anyways, so here's a free energy diagram. We show the reaction progress, and here's the free energy of the substrates versus the free energy of the products. Please pause the video and tell me whether you expect this reaction to proceed in the forward direction or whether it'll proceed in the reverse direction. Please pause and answer. Okay, now this is obvious, but let's be real clear. Anytime you see these energy diagrams, I hope you'll use my water analogy. This could be a mountain lake. This is a lake out in the plain. Which way does the water tend to flow? Well, it tends to flow from left to right. And so that is the tendency of the thing to flow, that energy goes downhill. Think of the boulder I drew on that incline that rolled down and smashed into a stump. When I talked about energy, it tends to flow downhill just like water does. At equilibrium, will there be more of the substrates A and B or more of the products C and D? Please pause and answer. And I hope you're saying, okay, this is too simple. Yeah, of course, there will be more of the lower energy one. In whether at the very beginning you have only C plus D, if you give them enough time to fully react and reach equilibrium, you will have a certain ratio of products over reactants. If you only start with A and B and let them react over a long period of time and they reach equilibrium, you will have the exact same equilibrium because it depends upon the relative energy. If you begin with an equal mixture of A plus B and C plus D, which direction will the reaction tend to proceed? And in fact, that's what these reaction diagrams stand for, is where you begin with equal amounts. And of course, at equal amounts, well, you're going to end up with more C and D, so the water tends to flow downstream. At the end of the day, at equilibrium, the mountain lakes always have less water than you have in the ocean. Now, I've been talking about the spontaneity, meaning whether or not the reaction will tend to occur in which direction, and given enough time, what that equilibrium will be. But you could have a reaction that could take 1,000 years. What part of this diagram determines the rate? Please pause and answer. Well, again, with the water analogy, it has to do with any type of barrier that's between the two energy wells. In terms of a chemical reaction, these energy wells are that the electrons are happy. They're in low energy wells, one of which is located high, such as in a carbon to carbon or carbon to hydrogen bond, where they're apolar, they don't really care where they're at, or they could be in an energy well that's low, such as a carbon to oxygen or oxygen to hydrogen bond, which are really polar. The electrons have fallen to the more electronegative atom. So of course the rate is that somehow you have to get between the two wells. Right now in the air around you, there's plenty of oxygen, you have plenty of carbon. Why aren't you exploding? We've already talked about that. The part of the diagram that matters is the peak. The very highest point of the diagram will decide how difficult it is for the water to get from one well to a deeper well. Now, in terms of a chemical reaction, what does the very peak, the very maximum of that represent? What's happening chemically at that time? It's real important that you pause and answer that question now. Somehow those electrons have to get out of the carbon to carbon and carbon to hydrogen bonds in order to fall to oxygen. So this is the point at which the bonds are breaking and reforming. Okay, so we have the two wells, we have the reaction occurring. What does an enzyme do to speed up the rate of reaction? Please pause and answer. Since the rate of moving from the high energy well to the low energy well is completely dependent upon the barrier between the two wells, the only way to increase the rate would be to lower that barrier. For example, if you have a mountain lake and a reservoir down in the plain, maybe you could dig a tunnel or a canal, and thereby you could go through a lower barrier and it'd be easier to move more rapidly from one reservoir to the other. In terms of electrons, how do you get the electrons in these stable carbon to carbon, carbon to hydrogen, hydrogen to hydrogen bonds, down to falling to oxygen to make carbon-oxygen, oxygen-hydrogen bonds? Well, the most important thing that enzymes do is positioning. Instead of having two different substrates randomly bumping into each other with who knows what type of rotation, orientation, positioning, rather the enzyme grabs both substrates and it positions them precisely. If this is a nucleophilic attack, it exactly positions the electrophile right next to the nucleophile with the correct orientation so that lone pair of electrons are sticking right towards, say, the partially positively charged carbon, and bang, the reaction goes. So we have orientation and positioning, and in addition, the electrophile or the nucleophile could be improved. For example, the electrophile may actually have a proton added to it so that it has even a stronger attraction for a lone pair of electrons. The nucleophile might have a proton pulled away from it so it's even more negatively charged. But before we get there, let's slow down. I want to be sure you get an idea. We're going to use real substrates, the very familiar reaction of ATP with glucose to make glucose 6-phosphate. And you could ask yourself, for the lone pair of electrons on carbon-6 to nucleophilically attack the phosphorus of the gamma phosphate group, they have to be positioned together. And in solution, this ATP could have any orientation, glucose could have any orientation. If they're precise, such as on an enzyme, you can do the nucleophilic attack, you can get the intermediate, the electrons can resonate back down, break the bond, glucose 6-phosphate and ADP. That is an enzyme precisely catalyzed reaction that's much quicker, a millionfold quicker than what happens in solution. In contrast, in solution, you hope that the ATP rotates in a particular position, the glucose does, and it positionally moves in, but all sorts of possible combinations, orientations, locations are possible for both the glucose and the ATP. And out of thousands of possible ways these two molecules can collide together, only one will give you that reaction mechanism. That's why in solution, reactions occur at such slow rates without enzymes. And again, the analogy I'm using is that the pink on this hexagon representing hexose represents the lone pair of electrons on O6. The blue on the rectangle here represents the phosphate. And in that case, the ATP and glucose can be bumping together with thousands of different ways at low and high energy. Only a high energy collision, which pushes that lone pair of electrons right into the phosphorus atom, is going to actually be productive. And that's why most enzymes increase the reaction rate a millionfold. So enzymes basically affect both the enthalpy and entropy terms in terms of favoring these reactions by positioning and by stabilizing the charges which would occur when the bonds are broken. I'm hoping you have a little bit of insight into the power of enzymes and how positioning is so profoundly important. And now I want to look at from the textbook some names of some different types of enzymes. You should be able to interpret each of these and get some idea of what they do. So go ahead and do that. Please pause and write each of these down and you'll go, oh wow, I don't have to memorize hardly any of them. But we're going to move on. So I would look at this and go, let's see, oxidoreductase. This is the type of enzyme that does an oxidation reduction reaction. In particular, if you have an oxidoreductase, do you think the first substrate in the name of it or the second substrate in the name of it will be oxidized or reduced? Please make a guess. So, an oxidoreductase oxidizes one substrate and reduces another. Normally, when you have an oxidation reaction, you have to have a reduction reaction for the slight difference in the electrons. An oxidoreductase oxidizes the first substrate in the name, and it reduces the second substrate in the name. Transferase. What general type of reaction does that do? Please answer. Wow. It is an enzyme that transfers a chemical group from one compound to another. Hydrolase. Please interpret it. Of course, you didn't need to interpret it because we've studied a few of these before. Hydro, of course, is referring to either hydrogen or water. In this case, it's referring to water. It is a water enzyme. It is an enzyme that lyses or breaks a compound using a water molecule which gets inserted into one of the products. Lyase. Well, now this one, I think it's clear, but it's not. There might be a little more memorization here. This lyse means to break something. So a lyase is just like a hydrolase, except this refers to lysis of any substrate without using water. Since you have hydrolase means you break a molecule apart using a water molecule, if you break a molecule apart through some other mechanism, it's called a lyase. Both of those are lysing or breaking compounds. Ligase. Please think etymology. Can you make sense? Ever hear of a ligature, like a knot? Ligases ligate things. They tie them together or link them together. Take two different substrates and link them into forming one substrate. Isomerase. What's an isomer? Please pause. You already know what an isomer is. An isomer of a compound has the exact same types and numbers of atoms and the exact same types of bonds, but just that they're organized differently. D-alanine versus L-alanine would be a good example of one. So an isomerase converts one isomer of a compound into a different isomer. I want to be sure you know that you do not need to memorize this list of enzymes, okay? I don't want you to memorize it. But even in the short couple of weeks that are left, I want you to be able to interpret every enzyme in this list. Now, focus on the most important ones, but how can you interpret them? Well, do not memorize them. That's the worst thing you can do. You're memorizing too much stuff already. Interpretation is fairly easy if you understand that there's an enzyme grammar. The first name in an enzyme is the substrate of the enzyme. It's the object or subject, the substrate. The second name in the enzyme is the verb or the activity. For example, alanine transaminase. Interpret the name and tell me what it does. It grabs hold of alanine and it transfers the amine group. When you transfer the amine group away from alanine, what do you get? Please answer. You know this from when you drew the amino acids. You get pyruvate. Likewise, aspartate transaminase transfers an amine from aspartate. And I believe I know you know what that one gives. So the point is substrate object. But let's go right now to look at kinases, because we've already looked at hexokinase. Kine gives you a clue for what it does. Does any of you know what a word that begins with K-I-N? This is based upon the word kinetic. Kinetic means active. Now, this is one of the slightly more obscure names or types of nomenclature. It requires a little bit more memorization on your part. But kinases are so important, it's worth thinking about it. The first kinase discovered was an enzyme that activated a different enzyme. So hence, kinase, an enzyme that activates a different enzyme. But it turns out later they figured out that the way the kinase activated another enzyme was by adding a phosphate group to it. It turns out that a phosphate's a pretty big group and it's negatively charged. So when the kinase added a phosphate group to another enzyme, that negatively charged group attracted some positively charged group on the other enzyme and caused it to change its conformational shape, and it opened up its active site so that it would now become active. Okay, so kinase. It originally meant that it was an enzyme that activated a different enzyme. It turns out that some enzymes, however, which added a phosphate group to another enzyme, inactivated them. Again, having a big phosphate group added to an enzyme that didn't have a phosphate to begin with causes a conformational change, and in this case, it either closed the active site or blocked it. So you can phosphorylate some enzymes and turn them on, and you can phosphorylate other enzymes and turn them off. For that matter, you can phosphorylate glucose, and that's not even an enzyme. So a kinase means an enzyme which adds a phosphate group to some other substrate, a sugar, another enzyme, whatever. And for example, hexokinase interpreted. Hexose kinase. It acts upon hexoses, such as glucose, and it adds a phosphate group. And where will you get a high-energy phosphate group? Almost always from ATP. Not always, but usually from ATP, and there's, of course, our reaction. By the way, the categories of enzymes we looked at earlier, what would hexokinase be considered? What did the enzyme do? Write a sentence to say what the enzyme did and then categorize it. You can look back at the categories. Well, it is a kinase, and I would say the earlier category, it moves a phosphate group from ATP to glucose, or it transfers a phosphate group. So this would be in the category transferase. I think it's more important to recognize that it's a kinase. And as we mentioned, when you take glucose and ATP, those are really high energy orbitals. And in order to add them, you need to position them precisely. You sometimes add positive and negative charges to lower the energy of the transition state, and bang, you go down. And the energy of glucose 6-phosphate and ADP is less than the energy of glucose plus ATP. Can you explain why that's lower in energy? I want you to do that. If you can't, I think you should give me a call. Basically, what I've been talking about is table 6.1 in the textbook. And basically, it's saying that you increase the reaction rate or you catalyze chemical reactions. How do you do that? You have to obey the laws of thermodynamics. What does that mean? Well, when you take an enzyme to speed up the transition between glucose and ATP versus glucose 6-phosphate and ADP, how will that at equilibrium affect the concentration of glucose plus ATP versus that of glucose 6-phosphate plus ADP? Please answer. The ratio of substrates versus products is completely based upon the energy wells that they're in, their relative energies, the free energy. The rate at which you interconvert between them is dependent upon the enzyme, upon the energy of activation. So at equilibrium, there's no change in the final ratio. Let's look at another enzyme. How about a dehydrogenase? What's so powerful about understanding enzyme grammar is look at, there are all these dehydrogenases, and they all catalyze essentially the same reaction. Glucose 6-phosphate dehydrogenase takes a hydrogen from glucose 6-phosphate. Lactate dehydrogenase takes a hydrogen off of lactate. If you understand enzyme grammar, then just any one of these substrates are being acted upon and a hydrogen is being taken off of them. Nothing should be easier than interpreting the name dehydrogenase regardless of the substrate name. Not brute force memorization of a whole bunch of gibberish, but simple read what it says. It's like the alphabet. Let's take a look at lactate dehydrogenase. Lactate dehydrogenase dehydrogenases lactate. So here I'm showing the hydrogen of interest on lactate, and you drive that hydrogen, that hydride ion actually, onto NAD. And we looked at NAD, nicotine, amide, adenine, dinucleotide, base-base, ribose-ribose, phosphate-phosphate. So that hydride ion is driven off of lactate by an oxidation because the single bond of the hydroxyl gets oxidized to a double bond of a ketone. And therefore, the oxidation of lactate to pyruvate drives a high-energy hydride ion with its high-energy electrons into high-energy orbitals in NADH. Now a trick, you can kind of memorize this, you may need help with this, is to say, oh, we know that hydrogen, carbon, hydrogen, hydrogen, they're all electropositive. So if you see an NAD plus and an NADH, you really don't even have to know all this chemistry to go, ooh, NADH is probably the high energy form because it can donate that hydrogen with the electron. A proton walks into a bar. Bartender says, "Why so down?" Proton says, "I lost my electron." The bartender says, "You sure?" And he goes, "I'm positive." Anyway, so the bartender says, "Hey, I tell you what, have a neutron on the house, free of charge." Now, there's a point in this joke. Whenever you're talking about pH, which we've talked a lot about, try to call that H plus a proton. A proton is very different from a hydrogen atom or a hydride ion because the hydrogen atom or the hydride ion has electrons. And those electrons fall from high energy hydrogen, 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 carbon, carbon, carbon orbitals down to molecular oxygen and form hydrogen, oxygen, carbon, oxygen bonds where they can lay low near the oxygen. So think protons, pH, think hydrogen atoms, dehydrogenases. Please go ahead and draw the nucleophilic attack. How can you tell where the electrons on this hydride are going to go to on the ring? Well, you look at the product and draw an arrow to show the movement of that bond, those two electrons in that bond, toward the nicotinamide ring. So again, a lone pair of electrons on the oxygen will resonate down to form a double bond, driving the two electrons in the carbon to hydrogen bond onto the nicotinamide ring. Now, what's really neat about the nicotinamide ring is it is a heterocycle with a nitrogen atom. Normally, the lone pair of electrons on that nitrogen in the heterocycle will resonate around with the aromatic ring. However, as the hydride comes onto the carbon, well, the electrons in the aromatic ring have to move. They can resonate over one carbon bond, which can push the next carbon bond over, which can go right up onto the nitrogen. So what has happened? The hydride has moved. You've lost aromaticity, but you have that nice lone pair of electrons on the nitrogen. Now, that lone pair would love to resonate back into the ring because aromatic electrons are really low in energy, which means you can push that hydride back right onto the pyruvate to go back to make lactate. This reaction can be drawn in either direction. Will you now draw the arrows to indicate the reverse reaction? please do so. The lone pair of electrons on the nitrogen can resonate to form the double bond. The other double bond in the ring can resonate up onto the carbon. The hydride can come off and be driven onto the carbonyl carbon as the double bond gets driven up onto the oxygen. So now we've looked at both directions. And again, you have to position the lactate right by the coenzyme. You have to position the pyruvate right by the coenzyme in order to drive this reaction in either direction. It is the positioning that lowers the energy of activation. However, the energy of activation is lowered even further by the position of a histidine residue in the enzyme right next to the lactate or pyruvate. Looking at the figure, will you tell me how that histidine further lowers the energy of activation? Please pause and do so. But I'm going to move on. The histidine ring has a lone pair of electrons which can pick up a proton near physiological pH. Its pKa is around 6. If you grab the proton off of the hydroxyl, you have excess negative charge. There's an extra pair of electrons which would love to resonate down. So by pulling the proton off, you're favoring electronically to get rid of the hydride. Likewise in the reverse reaction, the histidine has grabbed a proton off of the lactate. Now it simply can donate that proton back to the ketone. So a lone pair of electrons on the oxygen feels the partially positively charged hydrogen pulling electrons away from the double bond, making the carbonyl carbon a better electrophile to accept the hydride ion from the NADH. So again, these are the ways you lower the energy of activation. Is lactate high in energy or pyruvate high in energy? Is NAD plus high in energy or NADH? Please pause and answer. We know that when you oxidize something, you burn it. Lactate has this hydroxyl, which in pyruvate has been changed to a ketone. You've gone from a single bond to oxygen to a double bond. The pyruvate is lower in energy. And so interestingly, the lactate also has that extra hydrogen atom, which is a suggestion that it's higher in energy because things with hydrogen tend to be higher because hydrogen is electropositive. Likewise, NAD plus versus NADH, which would be higher, generally the one with the hydrogen. So far, I've described in detail how kinases and dehydrogenases work. And I've explained the mechanism and how to think about what they're doing. You need to understand both of them in detail in order to do all right on the exam and to have some understanding of how biochemistry works because they're so prevalent. Almost as important are carboxylases, decarboxylases, and hydroxylases. Can you interpret those names to tell me what they do? And again, I think it's going to be fairly simple. As I mentioned earlier, we have the subject or object, which might be glutamate, and we have the verb or the activity, decarboxylase. Or how about glutamyl carboxylase? You don't need to memorize this stuff. Interpret the names, as well as you can interpret hydroxylase. Notice, not hydrolase, hydroxylase. Fill in the blanks to describe exactly what you think they do, but I want to move on. A carboxylase is an enzyme that adds a carboxylic acid group to a substrate. A decarboxylase, I'm hoping you say, wow, this is pretty simple. You don't need to memorize anything the name tells you. It catalyzes the removal of a carboxylic acid group from a substrate. A hydroxylase is an enzyme that adds a hydroxyl group. This is very different from a hydrolase. A hydrolase lyses things. A hydroxylase adds a hydrogen and oxygen, a hydroxyl, an alcohol group, to a substrate. 17 alpha hydroxylase adds a hydroxyl group to a steroid. And you don't need to know this. It's, again, we don't need extreme detail. It turns out it adds it to the 17 number carbon on it. 11 beta hydroxylase adds a hydroxyl group to the number 11 carbon on something, a steroid. 21 hydroxylase adds a hydroxyl group to the number 21 carbon. So now let's look at these enzymes in detail, and we'll start with the carboxylase. So pyruvate carboxylase, as an example, grabs pyruvate and it adds a carboxylic acid group to it. You absolutely should be familiar with pyruvate because you make that from alanine with a transaminase, or, as we'll learn later, pyruvate is the product of glycolysis, a simple 3-carbon alpha-keto acid. You add a carboxylic acid to it, and we have talked about oxaloacetate. So there's basically like an oxalic acid group where one of the oxygens has been replaced with an acetate group. Now, the problem with this is pyruvate carboxylase adds 2 oxygens in a carbon, a carboxylic acid group to pyruvate. But where did the carboxylic acid come from? Well, it came from one of the coenzymes, biotin. Biotin can be activated with a carboxylic acid group, then pyruvate carboxylase can grab pyruvate and its carboxybiotin group, bring the two together, and catalyze the transfer of the carboxyl group from carboxybiotin to pyruvate to make oxaloacetate. Now, I should point out that in going from pyruvate to oxaloacetate, you did add a carbon-to-carbon bond because the carbon in the carboxylic acid has now been added to the carbon that was on the pyruvate. So I would say that goes up in energy. At the same time, in order to form it, carboxybiotin was activated with a carboxylic acid group added to that, such that if you look at carboxybiotin plus pyruvate and you compare their net energy to oxaloacetate in biotin, you will see that they are very similar in energy, which means that this catalysis could happen in either direction. Now, interestingly, in your cell, if you're running glycolysis, you keep making a whole bunch of pyruvate. And you tend to keep biotin in its activated carboxyl acid linked form. So you tend to have a lot of substrates, which then can get converted into products, which can then be depleted. So even though you tend to have them, even though at equilibrium, you should have equal amounts of the substrates and products in the cell, since you keep making a lot of carboxybiotin, and since you keep burning oxaloacetate, the reaction tends to occur mostly in the forward direction. Now let's look at a decarboxylase, and we will look at the decarboxylase that decarboxylates glutamate, an amino acid you're very familiar with. You can see the reaction here. In this particular reaction, glutamate gets decarboxylated by losing the carboxylic acid group, which comes off as carbon dioxide. Can you tell me whether this reaction tends to proceed in the forward direction or in the reverse reaction? Which is more oxidized, which is more reduced? Please answer. If you look at the compounds on both sides, you will notice that the carboxylic acid group in glutamate has 3 bonds to oxygen, a double bond and a single bond. After the decarboxylation reaction, you have carbon dioxide where the carbon has 4 bonds to oxygen. So this has been burned from having 3 bonds to oxygen to 4, so this has gone down in energy. And in particular, it's a fairly simple reaction to occur. the electrons on the oxyanion of the carboxylic acid can resonate down to form a double bond, and that can push the electrons off of the bond between the alpha carbon and the carbonyl carbon of the carboxylic acid, so that the electrons can resonate up onto the alpha carbon. That can grab a proton, and then you simply have an amine. Can you name this compound using the rules of organic nomenclature? Okay, well, let's see. It has how many carbon atoms? 1, 2, 3, 4. So that would make it butane, which has a carboxylic acid and amine group. What is the Greek letter to indicate the carbon attached to the amine group? Please figure that out. Well, the biggest atoms are the oxygens, so the number 1 carbon is the carbonyl, or the alpha carbon is adjacent to the carbonyl. So we have alpha, beta, gamma. So I would call this gamma amino butyrate, GABA. It's going to turn out to be a real important compound. And as I mentioned, since this is an oxidation, you formed another carbon-oxygen bond, the free energy has gone downhill. Normally, to pull a carboxylic acid off of glutamate, it's not going to happen because it takes a lot of energy to pull the electrons out of their orbitals before they can fall down onto the oxygen atoms. But the enzyme is going to grab this in aligned charges to favor the reaction and thereby lower the energy of the intermediate. Now I want to look at a slightly different type of enzyme nomenclature. The same rules are followed. We have a synthase and a synthetase. At this point, I want to be very clear because there's a little bit of difference in the nomenclature. Normally so far, the first part of an enzyme name was the substrate and the second part the verb. Now, glutamine synthetase, glutamine is not the substrate, rather it's the product. So the more general rule is that the first part of an enzyme name is the subject or object, because synthetase implies something being made. And what is made? The object, glutamine. So again, glutamine synthetase is the synthetase that makes glutamine, so glutamine is the product rather than the substrate. It turns out the substrate of glutamine synthetase is actually glutamate. Glutamate is very similar to glutamine, so it can be used to make glutamine by the enzyme glutamine synthetase. I want to point out also a subtle difference between synthetase and synthase. Both synthase and synthetase means it makes whatever the object or substrate is specified. The difference is that synthetase requires ATP in order to make the product. For example, glutamine synthetase needs to burn ATP in order to convert glutamate to glutamine. A synthase is an enzyme that makes something, but it doesn't have to burn ATP in that process. We take glutamate, and first of all, we add a phosphate to it. We burn a phosphate. Will that reaction go up in energy or down in energy? Well, again, ATP has those 3 phosphates all negatively charged and trying to pull away from each other. Easy to pass the end phosphate, the gamma phosphate, onto glutamate to make gamma glutamyl phosphate. Then the enzyme grabs an amine, and that amine can nucleophilically attack the carbonyl and kick off the inorganic phosphate. And thereby you have glutamine. Now you could not simply take an amine and directly attack glutamate to make glutamine. Why is that? Because glutamate has a carbon-oxygen bond versus in L-glutamine, you have a carbon-nitrogen bond. Nitrogen is less electronegative than oxygen, so this was a reduction. Glutamine is higher in energy than glutamate. So how do you get there? Well, you burn ATP, And now you have a high energy glutamyl phosphate, which is higher than glutamine. So ATP went down in energy to allow glutamate to go up in energy to glutamyl phosphate. Then glutamyl phosphate went down in energy by kicking off inorganic phosphate with all that free resonance, and it can move away from it, and that is how you got the energy to add the amine. And let's look at an energy diagram here. This is a picture of what I just described. Here, glutamate and ATP and ammonia are all happy. They're in an energy well, but when you burn ATP, you've gone down in energy, you've released ADP, and you phosphorylated glutamate. Now, again, this is all in a happy energy well, but if you take glutamine and basically this could be, you break the bond. It's just like hydrolysis, except it's with an amine. And the enzyme grabs the amine, positions it for the nucleophilic attack, the phosphate comes off, which goes way down in energy, and now you have glutamine. So to synthesize glutamine, you used energy. I just wanted to remind you with one more step that the glutamine synthetase, that first step where you hydrolyze ATP to make glutamyl phosphate, again, you could draw the nucleophilic attack of the oxyanion on the gamma phosphate to look at that. So for this Thursday's talk, I am going to now look at one more enzyme, a bisphosphatase. Interpret that. Bis, or bi, think of a binary code, phosphate, ase. Doesn't give you a lot of information. There's a fructose 1,6 bisphosphatase, a fructose 2,6 bisphosphatase. For that matter, there's a glucose 6 phosphatase. A real good example is fructose 1,6 bisphosphatase. Enzyme grammar, it acts upon fructose 1,6 bisphosphate. As we said, that will have two phosphates, and they're linked on carbon 1 and carbon 6. My question is, what does ase mean? What does it do? Well, it does something with a phosphate on fructose. And what is the name of an enzyme that would add a phosphate? That's a kinase. So we already know what adds a phosphate, and it burns ATP. What do you suppose this does? It hydrolyzes one of the phosphate groups. Will that go up in energy or down in energy? Please pause and answer. Well, of course, a phosphate linked to fructose has a linking oxygen, and its lone pairs of electrons won't tend to resonate in towards the phosphorus atom to let the electrons in the double bond resonate up on the other oxygen, because that leaves a positive charge on oxygen. Therefore, linking oxygens don't like resonance. When you break off the phosphate group, now those negative charges can smear out, resonate all over the place, go way down in energy. Anytime you cut a phosphate group off of something, it's going to go down in energy. You cut the gamma phosphate off of ATP, it plummets in energy, because not only do you have that additional resonance in the inorganic phosphate, but you allow the charges to fly apart. In this case, the energy goes down some. Fructose 1,6 bisphosphate has one phosphate linked to carbon 1, the other phosphate linked to carbon 6. When you cleave off a phosphate, this gives you fructose 6-phosphate. Again, this is not something you should memorize at this point. You should just be able to interpret the language. How would you know which one? Well, that's in a future class. Anyways, that's as far as I want to go today. I've given you some basic idea of how enzymes work, the energetics, and I've explained the nomenclature of enzymes such that you should be able to interpret enzyme names instead of memorizing them as if they are gibberish. Now I want to build on this a little bit, and that PowerPoint will be due Friday. But this one talk here should cover you for Thursday. If you have any questions, you need to call me. I try to explain these things in simple terms, but I know that you're learning this stuff, So if you don't understand it, if you're completely lost, if you just don't understand something, or if you just want confirmation that you do understand it, I hope to hear from you. And in fact, I was delighted to get maybe a dozen calls this weekend, and I enjoyed talking with everyone. Enjoy the weekend. Do the remaining video on Friday. Thank you.